That is extremely kind. Thank you. I need to record that and play it back in 5 years for my tenure committee or something. Yeah, I am really, really happy to be here. I have also been following the SEM for some time since this group here, and it really does feel like a intellectual home. I think embodying a lot of the values that Luke was talking about. So I was originally going to give a different talk, but I realized that I actually talked here last year and I didn't want there to be overlap. So it's fresh, it's all different stuff. And the other reason is that I'm doing a tutorial tomorrow on kind of models of theory of mind. This is kind of the project that I'm using as kind of the backdrop for that tutorial. So I thought I might just go ahead and give you a sense of what the science is. And then we can jump into kind of how we actually pulled off the modeling. Okay, so imagine you and your friend are in the kitchen preparing a meal together. So if your friend is a novice to cooking, it might be necessary to spell out every step, right? So this is Remy the rat and his kind of clueless human partner Linguini, which is a good name for a cook. So, Remy's an expert and he's like, okay, here's how you do this, you stupid human. You melt the butter, you stir in the flour, you do this, you do that. But something that's really cool about human collaboration is this ability to gradually leverage these kind of small amounts of experience to chunk together abstractions. In this case, once Linguini gets to be a better cook and he kind of understands that all of these steps go together, he doesn't need these kind of step-by-step butter, flour, whatever instructions. Remy can just say the word roux, make a roux, and the entire process can kind of unfold in Linguini's mind. Okay, so I think that's really cool. But how do people do that, right? So collaboration can be really hard, and we see that process fail a lot, right? When we have kind of miscommunications, they're often wrapped up in some aspect of that, where one of us kind of says a word or assumes that the other person is going to break down the task in the same way as we do, and something goes wrong. So in this paper, which is just going out the door as a journal thing, I have a similar problem that Manish has, that I always have a good cog sci paper, and then it's from, I don't know, 3 to 10 years after that I kind of finally wrap it up. But this, we were trying to argue in the cog sci paper that you don't just need to coordinate at one level, you actually need to coordinate at 2 levels. Okay, so first of all, we need to coordinate our concepts. So if we're gonna try to cook a meal together, we actually have to represent the procedures of cooking in the same way. So, there's these goals and sub-goals, like melting the butter, mixing in the flour, and so forth. And we need to be on the same page about that. But that's not enough. If we want to communicate, we also need to talk about these things in the same way. So we need to coordinate our language. We need to map the same words onto those abstractions. So in other words, we need to form new ad hoc conventions. And I think that this is a interesting kind of way of maybe pulling apart the questions of synchrony that Talia raised at the keynote at the beginning, where there's coordination happening here, but then I think the question is kind of synchrony at what level or something, right? So there's not just kind of one global synchrony, maybe there's multiple sub processes that can be more or less aligned. So this is maybe one way of trying to start breaking that, that down. Okay, so how do we do this in the lab? We began by designing a structured collaborative task where individual kind of procedural actions could be kind of plausibly chunked into abstractions to elicit this. And I'll show you, it's like a collaborative building task. Then we wanted to explain these results. We threw some NLP at it to understand how the kind of abstractions are emerging and how people are talking about these things differently as they collaborate over time. And finally, we wanted to try to be more rigorous about what we mean by this like dual abstraction or dual coordination kind of account. So we tried to like mash up two, I think, really exciting currents of modeling, which is why I thought it would be a good tutorial. So basically, like on one hand, we have this kind of wave of like neurosymbolic concept learning models. So these are, you know, used to do basically inverse graphics. So you, I'll get more into that, but it's basically a way of like representing a scene as a program that is like composable and stuff. And then, so that's kind of like the concept learning side. And then we also have like a language coordination side as a model of like social inference and theory of mind and stuff. So we're going to try to mash those up and make them work together. Okay, so what is this paradigm? So yeah, we couldn't get rats to cook, but we realized that, you know, this kind of task maybe captured some of the same intuitions. So we paired people up over the web, and Will McCarthy, other first author, made this really beautiful interface that is open if you want to adapt it for some other purpose. So we paired people up. We told them that they were either going to play the role of the architects or the role of the builder. And they had to work together to build a tower. Okay. So importantly, these roles were asymmetric. So the architect could see like a blueprint. They could see the scene that they're trying to build, but they didn't actually have the ability to place blocks. And the builder couldn't actually see the blueprint, but they had the kind of ability to control the block placements. So they had to work together. So we let them kind of freely chat in a text modality. So this is basically like instant messaging about these towers. So it looks like this. So here's an example of a architect sees this kind of silhouette, sends some instructions, and then the builder, as you could see, kind of clicks and places blocks in this like Tetris world. Okay, and then at the end, nice job, you get confetti. And people love confetti. You always got to put confetti as like the end of the trial because it's highly motivating. So they get feedback and see what they're supposed to be building if they're the builder, and see what the builder did if they're the architect. And you may have noticed this is kind of like an example from pretty late in the game. So I'm going to give you a sense of what actually happened. So we used hierarchically structured stimuli. So every trial had a pair of towers. Those towers were built out of 4 blocks. And when you look at how people are, so we designed the trial sequence. This is kind of like maybe more on like Emily's side of like very classic cognitive psychology experiment design. So we wanted to like counterbalance everything and presented these combinations of towers in a random order. So basically, the first 3 trials of the task, they see different combinations with which side the towers are on counterbalanced. And then they have these repetition blocks. So they kind of like go back and see the same scenes multiple times. So this is, yeah.
You can finish yourself.
No, I mean, that was the...
Two just like questions about the experiment. One is, does the builder see like the silhouette thing or?
Only at the end.
Only at the end?
Feedback. Yeah, the builder just entirely has to go off of the instructions.
And then is it like the architect gets the plan and then says something to the builder and then the builder does stuff and then you check? Or is it like continuous conversation throughout and like the architect can correct?
Yeah, so you can't unplace blocks. So we did decide to fix that. Mostly just to make our analyses easier because we didn't want to like look at undo operations and complicated things. So basically, like if they place something wrong at the beginning, they just have to do the best they can going forward. So it's like they get partial credit. So we use like a F1 score. So it's basically like the overlap of the silhouette with the things. So they can still like, yeah, even if the architect sees that they like did something wrong, they can kind of like do their best to salvage the rest of it. And then, yeah, but as you'll see, they were pretty accurate. Yeah.
For the blocks, can you place them arbitrarily or do they be like some kind of
Tetris physics? Tetris physics. So the Will has also done a lot of cool work, like doing more physically realistic, like intuitive physics, basically, where there's gravity and stuff, right? So like you can't put like a thing here if it doesn't have anything to support it. But this was like Tetris physics. So like everything has to have support, it has to be on top of something, but there's like no gravity. So stuff doesn't like fall over. And again, that was just to kind of like focus in on this kind of like structural stuff. Any other questions about the task? Yeah.
It was just those 3 towers. There was no variance on that. So
yeah.
They had a name, they could...
That's the idea. Yeah. So it's basically like a very, very small space of towers. So like probably by the time you finish these 3, you've noticed that like there's certain structure here. So this is kind of the statistical learning part, right? That you're kind of like, if this were like a configural learning vision experiment, you would have noticed that, okay, like these things appear in this configuration a couple times, and these things appear in this configuration a couple times. So that's kind of the chunking part. So we wanted to make that pretty easy to like pick up on. Okay. So that's the task. I'm going to show you what happens. So we were interested in the instructions that architects sent. So this is kind of the first like pass at like behaviorally seeing what was going on. So people started out pretty similar. So they would give kind of block by block instructions. So there's maybe some variation in how they refer to the blocks. So this pair was talking about like a horizontal block. There were some that said like the red block or the blue block. But they were kind of like fairly specific spatial instructions. And then by the end, what Tessa was anticipating here is that they are starting to send messages like this. So just like build another L shape. And there was some variance here. So like, you know, instead of an L shape, this one's like build a tall tower, like the tall tower, right? Where their partner just knows which one that is referring to. So to kind of quantify this better, this is the accuracy as a F1 score. So by the end, they're basically at ceiling. Even at the beginning, they're like pretty good at giving instructions. So this is like, you know, they're being very careful, which is why they start out using a heck of a lot of words. So on the first trial, it takes them about 60 words total across all the instructions to like get their partner to get this accuracy. But by the end, they're like down to 20 words and even better accuracy. So this is kind of like from a Shannon information theory kind of perspective. This is like a characteristic kind of pattern that I see across a lot of my work, where people are basically like reducing the like cost of communication somehow. Like they're increasing the channel capacity of their like communicative channel. They're able to like encode more information in fewer bits. Yeah.
Just about if you just introduce a new tower, but this tower was combination of previous shoot tower, what will happen?
Yeah, we designed that experiment, but we haven't run it. So you can say like train people on kind of like horizontal towers or vertical towers, and then you have a test phase where you put them together into a composite tower. So basically like you could either parse it this way or this way. The question was basically like, how are people going to generalize the conventions they formed to the new thing? So basically if they've like chunked certain motifs, they should be able to like decompose a new tower into those motifs and kind of build on that. But yeah, we haven't run that. Okay. So now we wanted to do some like real basic NLP. So this is like pretty, I should, maybe during questions, pull up a new plot that we made that's kind of cool. But okay, so the super simplest thing you can do is look at, okay, what are all the words people used at the beginning? What are all the words people used at the end? And how did they change? So just at the token frequency level. So you can see block, very, very big drop from the beginning to the end. So in the early messages, they were using block, horizontal, vertical, red, a lot more, and then they kind of dropped those out of their messages by the end. And then the biggest things that appeared from that weren't there at the beginning that increased in frequency was like C, L shape, tall. So these are just like some hints that maybe there's some kind of like shift in the level of abstraction. And to like actually get at that better, we got an independent group of annotators to go through all of the messages and count the number of block level descriptions, the number of tower level descriptions, and like basically these are instructions that only refer to the tower level without specifying like lower level components. These are ones that only refer to the block level, and these have kind of a mixture. So it's like place 2 horizontal blocks in a row and 2 on the side like an L, right? So that would be kind of like a mix one. Yeah. I think that like, it's possible that there were, like, I wouldn't make too much of that. Again, this is just kind of like qualitative. I think some pairs like probably started calling the shapes like, I don't know, like the one with the blue at the top or something. So I don't know. I don't have a great like qualitative analysis of that. The point is that like the blocks didn't get used as much. Yeah.
Kind of like pushing it further, like you say more abstract expression. And my question, like, what do you mean by abstract in that context? Because I can exactly in that way, blue can become part of a higher level of abstraction, but the word itself is the same word.
Yeah.
So that if you now do a compositional piece, then actually block can become a U block. It's a part of a bigger thing. So the word block will appear with a different level of abstraction later on.
Yeah. So that's why we wanted to like do this, right? Because like we didn't want to draw any super strong inferences like, oh, just because they're using blue, they're talking about blocks.
But it's like some NLP that would completely fail you moving forward.
Yeah. You mean like if you tried to analyze it just in terms of like
annotation of the word block with the word the same.
Yeah, exactly.
Change its meanings throughout it.
Yeah, exactly. So like, yeah, those kind of things of like the compositionality giving rise to something with kind of a qualitatively different meaning than its parts, I think is like an interesting effect that we could try to also annotate, which is like, you know, you could look at the cases where some of these words like horizontal were like used later in the task and be like, are they like contextualized in some way that has like shifted where they would like show up here. Claudia, do you have a question? Okay. Excellent. So, and as far as like, what do I mean by abstract? That's kind of the point of the model, is that we're going to try to be really like precise about what we mean by that. So we wanted to kind of so this is like maybe something we can talk more about in the tutorial, but I kind of broadly think about different kinds of computational work. And I think a lot of the computational work we've talked about here is kind of like methods for analyzing your data in kind of more sophisticated ways and characterizing phenomena in like more like rigorous terms that allow you to like talk about it as a certain like in terms of a model. So like your data like has certain geometric properties, or your data like reveals certain kinds of alignment. There's kind of a tradition that I was raised in of like, sometimes it's called just like cognitive modeling, or kind of like your model is supposed to instantiate like a hypothesis about particular like mental processes that are happening. And when you compare models, it's basically like theory, like this model is a better fit to the data. Therefore, it's like maybe evidence that like these processes are going on as opposed to those. So I think that we've seen some of different like approaches, but I kind of wanted to like flag that some just like as a kind of two maybe slightly different traditions. And I do both, and I think both are good. So like this was kind of meant to be a way of trying to write down what cognitive processes might be unfolding that kind of allow people to do this task. So going back to this intuition that it's not enough to only share concepts if you can't talk about it, or only share words if you've like grounded them in different concepts. You need kind of both levels to be coordinated. We ground these processes out in these two lines of modeling. So program learning comes out of the like program synthesis kind of computer science literature. So this is kind of like older versions of these are basically like, how can I come up with a program that like does a certain thing automatically? So it's like, I want some inputs and I want some outputs, and I want the computer to like discover a program that does that. But now it's neurosymbolic. So these are neural nets that produce programs that you can check actually do the thing that you want them to do. And if you want a name to go with that, the kind of version of this we're using is called Dreamcoder. So this is like a paper by Kevin Ellis and in Josh Tenenbaum's lab with Armando Solar. And on the language side, this is kind of like what's close to my heart. You need some way of not just like individually acquiring new abstractions, but making sure that you have good representation of what your partner thinks about what words mean. So this is kind of the pipeline. We have an architect that takes in raw scene input. So basically just like pixels of a tower grid. They encode that in their machine minds. They think of what the corresponding language would be and plan an utterance, and then they produce it as a message. Their partner, the builder agent, translates that message using their own representation of what words mean, encodes that back into a set of concepts in their mind, and then tries to execute it in the environment. So at the beginning and the end, we get things in the same modality. So you basically have like raw stuff here, raw stuff there. You can compare whether they're the same or not. And the important thing here is that all of this agent's head, all of this stuff is happening in the other agent's head, and they don't have access to the other agent's head, right? So this is like the problem of social coordination, right? Because like, I don't know what concepts or language is in your head ahead of time necessarily. I can make guesses, but then I have to also like update my beliefs as I interact with you. Okay, so the other way of cutting this is like this. So what I showed you here is just a static model. So given some choice of concepts that we're going to write with this curly library notation and some parameterization of language that we're going to write with this phi symbol, we can run this forward. So the library would look something like this. You encode this as like, okay, I can produce this tower by, you know, running my f function, which maybe produces that, moving my like hand or something. So I'll go into more about what the symbols mean, but basically like these are two ways of writing this as a program. And then there's some stuff here, which is like, okay, this function corresponds to this language in some probabilistic way. So given a particular choice of this, we can just run it forward and pass in a raw scene and get out a set of towers. So that's kind of, go ahead.
So what's learned and what's kind of set in?
Exactly. Okay, so what's learned is the kind of content of the model. Okay, so what I was trying to say is like that by itself, there's no learning yet. So this is like with a fixed choice of these things, we can get input-output relationships. But the thing we're interested in is coordination. So we have basically two parallel learning models. So there's some learning happening at the level of what library you're using, and there's some learning happening at the like lexicon you think your partner has in their head.
Yeah, I was kind of wondering, is that in a way that seems to be like the convention formation part seems to be pure inverse learning in a way. So B kind of decodes what H and B and everything are based on these words. Is there any kind of integration of these already existing library or convention and all these kind of things in there so that it's, for example, that a misunderstanding could happen because I have a concept of these things?
Yep. So basically like the gap here is that I might be using a different library than you, but when I'm decoding the message, I have to like use the things in my library, right? So that's one example of that, where like I have a particular library that's accessible to me at a point in time. I hear a message, I'm trying to decode it and interpret what the words mean, but like this is the set of primitives that I am working with. So if that's different from the ones that you intended, then we might have a miscommunication. Okay, so how am I doing on time? When is it supposed to be over?
we're over time,
Okay.
but I mean, how much more would you like?
Honestly, this is just like, I was gonna unpack these, but I think that maybe I'll just skip to the results and then call it a day.
Maybe sums up get into the C4.
Yeah, totally. So yeah, mostly I just kind of wanted to like sketch out this like idea that there are these like two layers that each have kind of a learning process that we can write down. And then yeah, in the tutorial, I have like Python notebooks that do this. So we can walk through those. Okay, so the results here, we can simulate. We have Dreamcoder running, and basically it's doing like configural learning. So this is very classic like vision science, right? So you see some examples and you try to abstract out what they have in common. And it kind of acquires these tower level chunks by like somewhere in the second block. And then kind of like has those accessible to it. And this is obviously hiding a lot of details that we can talk about. And then on the coordination side, there's this idea that the architects, so we use this kind of like pragmatics model where the architect is trying to be informative. So they're trying to say something that the listener can actually understand and will like build the right thing, but they also like don't want to be too verbose if they don't have to be, okay? So if you put those two constraints together, you get this kind of signature effect where gradually, even if the speaker like has a tower level representation available to them, they may have some uncertainty over if I say that, are you gonna know what I mean? And you may not. So it may be safer to like stick to the blocks or stick to a combination of blocks in the towers. But like, as we interact more and I get feedback that maybe you do understand what I mean, and I'm more confident that we're aligned, I can shift more to these more efficient tower level descriptions. So we have kind of a model comparison. If you lesion the library learning part, you don't get this because you kind of like don't have the library to hang the words on. And then if you take out the social part, basically accuracy tanks, because like you're trying to use these abstractions, but like aren't coordinating on what they mean. So just as like a pitch, I'm kind of think that this is like a fun paradigm. So we've gone on and collected these like massive data sets with people giving instructions in natural language for like 1,000 different kind of complicated building structures that are kind of like bridges and skyscrapers and stuff like this. And also this like, we call it Gadgets 1K, which is basically like CAD drawings. So you're trying to like give instructions on how to like make a little CAD sketch. And these are like furniture, but we also have like little TVs with antennas and stuff like that. So all of these kind of expose like different abstractions that people are using when they're like decomposing it, where rather than being like, put two circles and then under that a big rectangle and then in the middle of that a smaller rectangle, like that works. You can convey it that way, but like people will instead be like, okay, draw a dresser with like two, round knobs. And then it's like, okay, you can then try to map that onto the things in the library learning and be like, okay, like the word knob corresponds to like this thing that the library learning abstracted out, which is like placing some parameterized number of little circles. Okay, so that's it. I will want to thank my collaborators. I'm not at Princeton anymore, this old slide, as of like a week ago, I guess. So I'm at Madison now. But yeah, thanks for your attention. A little time for questions. Okay. Mm. Yeah, I think that complexity is like, so one way I think that is maybe an even bigger difference is that we let people use natural language here. So I would actually argue that the task is more complex. So like if you tried to do this task where you only got to wiggle like rectangles around, it would be harder, right? That probably harder than like Arden's task, right? But like, because we gave people the ability to communicate, that kind of like became part of their coordination system that they were using to align themselves. So I think that like one idea is that this kind of abstraction actually allows you to tackle more complex tasks. So there's like a interesting results. So we always find these curves where, you know, people use fewer words and get better, but that's because the task was fixed, right? So my collaborator, Yoav Artsy, has this like fun project called Serial Bar. It's like very much an NLP thing. It's like not a good psych task at all. It like doesn't make sense as a psych task actually. But like they basically have it set up where you can, like, as you get better, it gives you harder tasks. And there they actually don't find this decrease. They actually find pretty constant like amount of information, but people are doing harder and harder and harder tasks. So they're able to like bootstrap on this, but instead of like doing the same task more efficiently, they do harder tasks at the same level of not, you know, like that efficient. So I think that that's like an important knob that we should think about. So there's kind of a question of like, and yeah, in Aryan's task, they also kind of curricularize it, right? Where they've kind of like designed the trial sequence so that at a certain point, like a strategy that worked before doesn't work anymore. And we could do that too, right? We could like suddenly swap out the towers at like trial 10, right? And then people, it's gonna like force people to do an aha thing where they have to like switch up their strategy. Yeah.
Really fascinating stuff. The thing that keeps in my mind is how are we really able to separate conceptual alignment from alignment and labels? So the way that you presented it, it's almost like the labels are hanging onto these conceptual labels that are already defined. Whereas in real life, the structure, the sets of labels that we're using, they're providing information about this conceptual structure, even if you don't get any sort of feedback, right, on whether other people are aligned or not. So kind of how can you maybe model or theoretically understand the sort of like dependent relationship between signal spaces and conceptual spaces?
Yeah, that's really important. So I put kind of a plus here, but you could also put like arrows going back and forth. So I think that like so I've been talking to like Gary Lupion about this, like language and thought people, where like, this is like a bootstrapping thing. So it's like new concepts require new language to talk about them because there's new meanings that you're trying to communicate. But then like, once you have those meanings, it also like gives rise to new concepts or like helps a learner maybe acquire concepts more easily. Because like, if someone's like, make a roux, and you're like, what's a roux? It like immediately gives you this, right? So it's like exposes this as like an important abstraction if you're trying to understand what this word means. So I think that, yeah, it's like a bi-directional process, and that's like not in our model right now, but it's important. Eshin, sorry.
Actually observe any instances teaching of the having like a viable strategy seems like in the beginning, let's get on the same page.
Yep.
tower is that block.
Mhm.
Did you see that or really don't? I'm curious why people don't.
Yeah. So I should say that we see a sprinkling of that in kind of all of our tasks. So like some people are like planning like better and they're like, okay, let's call this one a whatever, like in the tangrams task. Sometimes there's like this kind of explicit like, okay, if that one comes up again, let's call it Frank or something. I don't know. And then sometimes they just forget. So it comes back and they're like, oh, shoot, what did we call this one? So that isn't always the most effective strategy. Sometimes having like a space of primitives that you can kind of like reuse across different ones is like more effective. But I think the other thing that affects that is like how open-ended the task is. So I think that like at a certain point, it becomes clear that these things are cycling back again. And that kind of like repetitive structure, I think, is what like licenses that kind of strategy. Whereas like Ricardo Fusaroli, Kristen Tylen at Aarhus have done some nice studies where they manipulate the open-endedness of the stimulus domain. So basically, like if you just keep introducing different towers, like that strategy just completely doesn't work. And people instead they come up with a more kind of like, I don't know, like they carve the joints of the thing, right? To be like, okay, what is like a way that we can like generalize well? So I would say that there's kind of like the environment that you put them in creates like a functional pressure toward either like memorization versus like generalization. And like the kind of repeated reference games, we're actually interested in the way that like, you can explicitly refer back to the way you talked about the same thing. But if it's open-ended, then yeah, you get these really interesting other strategies. Yeah.
Yeah, so the fewer words are used every time, but I'm very curious, like on the very first trial that you see more variability there, like some assumed shared traction, and then you see a lot more words after like a failed trial.
Yeah. So on the first question, yes, you see some mixed stuff even on the first round. So that's basically people who are like giving a long description in terms of blocks and then kind of a pin to that at the end. Like, actually, it looks kind of like an L, right? And like their partner doesn't entirely have to go off of the L, but they're kind of tagging it as like, by the way, like this is another way you could think about it. But obviously, like not everyone's doing that. Some people are just like block, 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 block. Cool. So to your second question, I don't have this for this presentation, but this is actually one of the things we were talking about last night, is in this other task I use, which is like this tandem task. There is this very clear thing where like you don't reduce your description if your partner gets it wrong. And it's not actually just the trial after it. It's like when that one comes back around, you don't reduce it from the previous like 5 minutes ago. So that's actually like not just like local cues. It's like, okay, I have uncertainty about like, clearly you didn't understand what I was saying about this particular object. So I'm going to like try a different tack or like maybe use more words even. Yeah. Yeah. Definitely. I mean, I was gonna say this is like, I don't know if I could find this in time. Maybe I'll try. But I have it right here. It's like stuck it in this paper. But some people kept using blocks all the way to the end. So those are people that kind of just like found a strategy and stuck to it, which I can sympathize with, you know, they're like, why, if it ain't broke, don't fix it, you know, like we're doing a good job. The figure I was looking for is here. So this was like a more recent, like TSNE kind of analysis that we did. So we like took the things of all the descriptions people used. Each line is a game. And this is like what they said at the beginning to what they said at the end. And you see that there is this like big shift from kind of like block world to shape world. So like a lot of people start over here and go up here, but then, or start with horizontal, vertical and go here. But some people actually went in this direction. So they just like doubled down on simple block level descriptions. And some people even did like weird stuff, like came up with like a coordinate system or something, right? So it's like C1, L2, like, you know, like they're doing Minesweeper or something. So it's like, and you know, like going back to Eshen's point, like in a different task, that would actually be the most efficient. Like if we were just showing them random grids, that probably would be like an optimal strategy. It just like, yeah. So this is like the point of conventions, I guess, is that there's like multiple equilibria, and it kind of just matters like what, as long as you and your partner agree on it, it kind of works. But it would be interesting to look at like whether certain pairs like converge faster, or like even by like the second repetition, we're already at like 4 words or something. And they might have done something like Eshen mentioned, where they're just like, let's call this the L. And then it comes back and they're like, the L. Yeah.
With chess and Greek, right?
Yeah, exactly. No, I mean, these are, you know, notation for music and stuff, right? That, you know, we don't use words to tell a piano player how to play. We like compress it down into this like other symbolic system. So I think that like you could, if you're like, I guess, trying to be careful here. If you're like inclined to make grandiose claims, you could say that like, that's like the birth of a new like language or something, you know, but like, I think that like these kind of systems that people are coming up with, they're kind of, we call them like temporary or like ad hoc conventions, because they're kind of like developed for this task. And then like these participants are never going to use that again. Basically, it's like a disposable temporary meaning system. But then like in other cases, like if you're developing an experiment and you're like, okay, let's call this like the no shadow condition or whatever, then you kind of like keep using that with your collaborators. And it's like your like little inside, you know, way of referring to the task or whatever. And in that case, it's like not temporary. It's kind of like useful for an extended period of time. Yeah, any other questions? I think we're probably, yeah. Okay, last question.
Yeah, great, thank you, yeah.
Yep. That's a great question. So like, yeah, this is, you could say like task-oriented communication. So this is kind of like, you have a very specific goal that might be like, if you were, yeah, like in, I don't know, like in a math class and are trying to like solve a problem or something. But yeah, I think that the kind of interesting thing about conversation analysis is that like, people are constantly sub-goaling in communication. So like if you read like the old Italian semiotic stuff, it's like they are kind of like laboriously annotating casual conversations for like, okay, this person like this line like introduced this new question under discussion or whatever. And now there's kind of like this sub goal thing. So it's like, you know, if I'm like, oh, where are we meeting tonight for dinner? And then someone's like, wait, I didn't know we were having dinner or something. Now, like, there's a question of like, how efficiently can you resolve the, wait, I didn't know we're having dinner, and like get back to the main thread of the conversation is one way that you might think about that. So it's like, and then these can be nested where it's like, wait, I didn't know we were having dinner. And it's like, wait, I thought I invited you. And then it's like, no, you didn't invite me or something. And then you have a whole argument about like, you never invited me. And then like maybe 5 minutes later, you're like, okay, fine. Like we're friends. Like, and then you kind of like pop out and you get back to stuff. So yeah. Okay, thanks.